This is the last lesson on topic 2.1. What we're going to be looking at here are angled projectiles. Then we're going to move into the projectile graphs. These are similar to the motion graphs we talked about earlier. However, we're going to be looking at it on both the x and the y axis. Also going to introduce you to a fourth graph type, which is the position graph. This is simply a motion diagram in 2 dimensions, and then we'll finalize with, again, with the impact of air resistance on projectiles. First off, just to remind you, for all projectiles in the IB program, air resistance will be ignored as long as we're talking quantitative analysis, numerical analysis. Qualitative analysis may include air resistance in terms of the graphs, the trajectory, the graphs involved, okay? And for our angled projectiles, I'm going to break angled projectiles into 2 subcategories. The first category is the easier category, and this is the primary angled projectile that the IB will focus on. And this is an angled projectile on level ground. Non-level ground is when you start higher and land lower, or vice versa, start lower and land higher. Okay, this non-level ground problem is slightly more complicated, but as long as we follow the same rules, and we can analyze those just as well. Okay, the level ground problems are slightly easier because they start and they land at the same height. What that means is my displacement on the y-axis happens to be the same, okay, or actually is 0 for displacement. Okay, so that gives me an extra value that I can fill in on my XY table that we talked about in the previous slides. Non-level ground ones are going to be slightly harder, but still solvable. So let's look at the angled projectile. Frequently, when we have an angled projectile, your velocity is going to be given to you in magnitude angle or magnitude direction format. For example, the football is thrown at an angle of 35 degrees at a speed of 25 meters per second. Okay, and since it gives me a picture, the angle is going to be our standard positive 35 degrees. Okay, it's important to realize that this is in magnitude direction format. Don't simply take that magnitude of 25 meters per second and apply it to the x and the y axis. Okay, we must convert this into component format. Okay, the x component is 25 times the cosine of 35 degrees. The y component is 25 times the sine of 35 degrees. Okay, those components are what will go into our table, not the 25 meters per second. Okay, we have the same 2 vector formulas, okay, the v of t and the d of t, okay, velocity as a function of time, position as a function of time, okay, and those are given in the upper right hand corner in American or the format that we use in this class. You need to make the translation for the IB versions where u is substituted for v sub I, okay. Remember when we analyzed this in the horizontal projectile case, the x and y axis are independent of each other. And that's going to be important because then we can split up our x-axis and our y-axis. And so here's our x and y table again. Okay, the same 4 variables because v and I, the initial velocity and final velocity are duplicated. And the same 5 variables on the y-axis. Okay, my acceleration, it's still a projectile, it's still on Earth. Still going to be 9.8 meters per second squared downwards. So I know what my acceleration in the x direction is. I know what my acceleration in the y direction is. Okay, I can go ahead and fill those values in. Okay, so let's start here. Okay, my acceleration on the x is going to be 0 meters per second squared. And let's treat it in the standard format. So this is going to be 9.8 meters per second squared. Okay, so when we talk about how far this projectile goes, okay, we're talking about the range of the projectile. The range of my projectile is the horizontal displacement, okay? It's not the total displacement on the angled, okay? It's just on from the base or origin on the x-axis to however far it goes on the x-axis. Okay, on level ground, it's pretty much where I start to where I end. Okay, my vertical displacement will be 0 meters. If the ground isn't level, pay attention to that positive minus. Okay, if I define positive as upwards and it lands lower, my displacement is negative. Okay, final minus initial. So here's my table filled out for my sample problem, okay? On the x-axis, I know what my initial velocity was, okay? My initial velocity is given here, 20.5 meters per second. That's the same velocity we had back here. There's my 20.5 meters per second. Okay, and here's the other one, okay? My initial velocity on the y-axis is 14.3. Okay, same 14.3 that we calculated here. Okay, whoops, too far. Okay, here's my 9.8 meters per second squared, and here's my 0 meters per second squared. Okay, the reason I have this value filled out, my final velocity on the y-axis being 0, is because I'm looking for maximum height. Okay, remember at the maximum height, the vertical component of my velocity is going to equal 0. Since my maximum height equals 0, my vertical velocity equals 0 at that point, I can put that value in. Now I have 3 variables in my y column, 1, 2, 3, and I can solve for my displacement on the y, which is what I'm looking for the maximum height. If I was looking for the maximum distance, okay, if I was looking for maximum distance, that's an x-axis discussion. I would then set I could not at that point use my y velocity equal to 0 because it wouldn't equal 0. My displacement on the y, however, would equal 0. Okay, so again, I would start by analyzing my y-axis if I was looking for my range value. So that brings us to our various graphs. Okay, our position time graph, our velocity time graph, and our acceleration time graph, just like we talked about in the earlier set of slides. Okay, but now we're going to have 2 sets of graphs, one for the x-axis or horizontal axis, and one for the vertical axis or y-axis. Okay, remember, as long as I ignore air resistance, my horizontal position is going to show a constant velocity. So it's going to be a straight line with the slope of my line equal to that constant velocity or v of x. On my y-axis, okay, what's shown there is a level ground, and in this case, the object goes up, comes back down. Okay, this vertical position is going to be a parabola. Okay, dy is equal to v sub y. I'm missing the letter t in there. Okay, v sub y t minus 1/2 gt squared. Okay, so the shape is not going to be a straight line. I have acceleration. My acceleration is downwards. Okay, so look for these 2 graphs and understand, which one of these is the vertical, which one of these is the horizontal. Okay, the velocity time graphs are just the slope of those graphs as we know. Okay, in the first case, my horizontal constant velocity is just going to be a straight horizontal line. Okay, that makes sense because the slope of the horizontal is going to be my acceleration on the horizontal. Slope is 0, acceleration is 0 on the horizontal. If I wanted to know my displacement, okay, I would get that from the area under the graph. Okay, this is the displacement for the first unit of time, and then this, until I have the full displacement at the dotted line time. Okay, on the vertical side, okay, this is the same thing. Okay, my projectile starts with a positive velocity. Here it is, positive velocity, hits a peak, okay, where my velocity goes to 0, and then lands at pretty much the same one. Okay, so this looks like a level ground graph. Okay, and the slope of this graph is my acceleration, or in this case, it should be minus 9.8 meters per second per second. Okay, and if I wanted to know its velocity, I have to do area under the graph, or actually it doesn't give me my velocity, it gives me the change in my velocity. So here my velocity from the beginning changes. Okay, until, sorry, the area under the graph gives me my displacement. So my projectile clearly goes upwards because I have a positive displacement. And then under the x-axis, I have a negative displacement. So at the end, my total displacement is 0. It landed at the same height I started on the y-axis. So the last graph is our acceleration time graph. It's not very exciting. If I looked at the horizontal one, it's just the horizontal line on the x-axis. Can't even tell it's there. But horizontally, my acceleration is 0 meters per second squared. Vertically, assuming that I have the standard coordinate system, my acceleration is going to be 9.8 meters per second squared, negative. Okay, just constant acceleration. This is the last graph, okay? The last graph is a position graph. Look at those axes, okay? On the x-axis, I'm in meters. On the y-axis, I'm in meters. This is a position graph, okay? The slash is IB's method of labeling their axes / units, okay? Axes / units. So that's why it's x / meters, y / meters. This is nothing more than a motion diagram, okay? Each dot is evenly spaced, okay? 1 second apart, 2.2 seconds apart, 10 seconds apart, okay? So this would be at like 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, okay? We can graph these if we wanted on a regular position time, velocity time, acceleration time graph, okay? But we can pull a lot of information out of this graph and perhaps plug those into the formulas. Because we have a time axis, okay? The time axis is given by this sequence of dots, okay? And I basically know my x position at 0 seconds, 1 second, 2 seconds. So I can effectively calculate my horizontal velocity. It's constant spacing, okay? This should be the same. Constant velocity on the x. Okay, if I was to look at the y-axis, okay, let's choose a different color, green. Okay, if I look at the y-axis, it's a slightly different story because I have acceleration. Here's my y, less, and then here I'm back again, and then back again, and then lower. Okay, so I have acceleration on that axis, but I can still graph it as a parabola. Okay. As a position time, I should be, as long as I'm on Earth, I can calculate my acceleration. I have a maximum height here given, so I have a lot of information that I can play with here. Okay, and so a position graph, you need to be able to recognize that, realize it's a motion diagram, realize that you have a time axis given on this type of graph. Okay, last off is the impact of air resistance. If I ask which ball will go farther, a ball thrown without air resistance or a ball thrown with air resistance, almost all of you would say the ball without air resistance will go farther. So that's easily understood. Okay, but when I look at graphs, I see a lot of confusion because I get different answers sometimes. Okay, the air resistance graph will always be within the no air resistance graph. Okay, so it won't go as far. So the red graph here, okay, is with air resistance. Notice it doesn't go as far. Okay, the blue graph goes much farther. But that's also true in the y-axis as well. Okay, the y-axis without air resistance versus the y-axis with air resistance. Okay, it won't go as high or as far. The air resistance graph as well will not be symmetric, okay? This time, okay, is a little bit less than 40 seconds, okay? But this one is about 75, actually about 70, okay? It's not going to be a symmetric graph, and it's always going to be within the no air resistance graph. It will never go farther, okay, outside that graph. And just remember that about air resistance, okay? It'll never go as far or as high, okay? And just to summarize, okay, when the projectile is on level ground, we have a couple of points that are symmetric that we can use, okay? And the point that's important to remember is that the maximum range on level ground is going to be achieved at 45 degrees. Okay, and it's going to be symmetric around that angle, okay? If I'm this range at plus 45 plus 5, 50 degrees, is the same as the range at 45 minus 5, or 40 degrees, okay? 30 and 60, any complementary angle will have the same range, okay? And the maximum range, these arrows are wrong, okay? This should be a less than, and this should be a greater than. Okay, the maximum range is going to be achieved when it's when my displacement is lower than I finish. Okay, dy is less than 0. In that case, my maximum range will be achieved at an angle greater than 45, and vice versa if I start higher. Okay, and just to remind everybody, okay, for a level ground projectile, the trajectory is going to be symmetric. Okay, the time that it takes to go up is the same amount of time it takes to go down. My initial angle that I start out is the same as the initial angle I come down at, except it's from the minus direction. Okay, same with my initial velocity. The magnitude of my initial velocity is equal to the magnitude of my final velocity. The only thing difference between those two is going to be the direction. Okay, because when I launch it, my y-axis is positive, and when I land, my y-axis will be negative. Thank you.